Hi, I'm Gina. I just finished my PhD, and the topic of my dissertation was internet connection splitting. This idea was really big in the 1990s, and it was really important for improving the performance of the internet. But recent developments like the QUIC transfer protocol and the BBR congestion control algorithm have now made connection splitting impossible and maybe even unnecessary. In this presentation, I'd like to talk about how we should think about connection splitting in our networking research today. And this is a collaboration with Thea Rossman and my advisor, Keith Winstein from Stanford University. So what is connection splitting? Imagine you're on a moving train. Your laptop is connected to the internet via two very different path segments. The first is a lossy, low delay path segment to the access point on the train, and the second is a more reliable, high delay path segment to the rest of the internet. Your connection is very slow because traditional congestion control algorithms, such as TCP QUIC, treat this wireless loss as really bad network congestion. With a connection splitting TCP PEP, or performance enhancing proxy, your end-to-end TCP connection is actually two independent split TCP connections without your knowledge. This allows the network to transparently tailor your congestion control on each path segment, achieving much higher throughput and generally better performance. Connection splitting PEPs are still widely deployed today. But a lot has changed since the 1990s. First, QUIC made connection splitting impossible. For privacy and security reasons and reasons related to allowing the protocol to evolve over time, modern transport protocols such as QUIC now totally encrypt their transport headers. However, PEPs rely on unencrypted information, such as the sequence number, in order to transparently help TCP, making it impossible to help QUIC in the same way. Otherwise, QUIC is very similar to TCP in that HTTPS traffic is a major application for both of these protocols. Second, BBR has, at least allegedly, made connection splitting unnecessary. BBR is a new congestion control algorithm that de-emphasizes loss as a congestion signal. When we recently presented our research on connection splitting at the IETF, we received feedback that all of this work was actually now moot with the adoption of BBR. As this comment reads, when AWS switched to BBR 2 to 3 years ago, the throughput of mobile networks with PEPs either declined or a steady trend, while those without had a significant increase in throughput. Thus, it seems that some think that BBR has kind of solved the problems that connection splitting was meant to address. So in the final months of my PhD, receiving feedback like this about my research, I started to become worried that my dissertation topic was already out of date before I'd even written it. So in response, we conducted a measurement study and wrote this paper to answer the question, did BBR and QUIC make connection splitting obsolete? And fortunately, we find it's a little complicated, and hopefully my thesis still has some good ideas in there. So in the rest of this talk, I'll discuss the three main findings from our measurement study, as well as the experiments that led to these conclusions. So in this study, we evaluated a variety of congestion control schemes. A congestion control scheme consists of a protocol implementation. The ones we looked at include Linux TCP, the Cloudflare and Google implementations of QUIC, as well as a QUIC implementation called PicoQuick that they use for experimentation in the IETF. As for the congestion control algorithms, we evaluate QUIC as our loss-based algorithm, as well as 3 major versions of BBR. In each of our experiments, we first pick a congestion control scheme, such as Linux TCP, BBR, v3. Then we emulate a 2-segment network topology using TCNetM, where each of these 2 path segments are configured by their bandwidth, a random loss rate, and a delay. And then finally, we download a large file over HTTPS, and we compare the throughputs of this file download, both with and without a connection splitting PEP. And what we want to see is if this PEP improves the throughput when we're using BBR or QUIC still. I want to be upfront with the limitations of our study. This study is done entirely in emulation, as opposed to the real-world internet. This gives us a more controlled environment, but it has we're not as able to directly extrapolate to the real world. The only metric that we measure with regards to performance is long-lived full throttle throughput of a large file download. Congestion control behavior is the main contributor to this metric, but connection splitting can also affect other metrics, such as the latency of a short file download. The third limitation is that all experiments are run in a single flow environment, simplifying the behavior of these congestion control schemes to control for interactions with concurrent flows. All right, The first finding is that in this network scenario here, TCP BBR has actually benefited more from splitting over time. Similar to the scenario on the train, the loss-based QUIC algorithm benefits significantly from splitting as expected. Now, anecdotally, with BBR v1, as suggested, the split throughput with BBR v1 has remained steady, with and without a PEP. However, versions 2 and 3 of BBR do not perform so well in the end-to-end scenarios anymore, showing that connection splitting actually does benefit BBR again. The reason for this regression is that new versions of BBR have reincorporated loss as a congestion signal because there was some controversy about its TCP friendliness. And in fact, Google now recommends older versions of BBR be deprecated in favor of v3. However, that was just one network setting. Does this generalize to other network settings? But to evaluate a variety of split network settings, we'd have to run emulations for all of these combinations of split network paths. To avoid this, we developed a heuristic for estimating split throughput based on the end-to-end behavior of a congestion control scheme. This allows us to run much fewer emulations. So the split throughput heuristic just takes the split throughput to be the minimum of the measured end-to-end throughputs on either of the two path segments. To see how we use this heuristic, first, we cache a variety of end-to-end measurements for a single congestion control scheme in a heat map. This heat map represents the proportion of link rate utilization for a variety of loss and delay values at a fixed bandwidth. And this one is for TCP QUIC. We can see that TCP QUIC achieves high link rate utilization when either the loss or the delay is low, but not when both are high. To estimate the split throughput, we identify the cells that correspond to either the two path segments, such as these two here, and then the heuristic just says that the split throughput is the minimum of these two cells, so 0.77. To estimate the end-to-end throughput, we first find the cell that corresponds to the network path that we get when we compose these two individual paths. The composition is simple. We just take the bottleneck bandwidth, add the delays, and then combine the random loss rates. So in this case, the end-to-end utilization at that cell is 0.04, showing that in this network setting, the throughput is actually much higher with the connection splitting PEP. Using this technique, we can estimate the split and end-to-end throughputs of a variety of combinations of split network settings without running so many emulations. So using this technique, with only 150 emulations, we can filter the results for almost 8,000 different split network settings. And in this analysis, we find that TCP BBR v3 actually even benefits in some types of network settings where QUIC did not before. So I'll go through each of these classes. The first class of network paths resembles the scenario on the train with one lossy low delay segment and one reliable high delay segment. It's asymmetric in the sense that the PEP is much closer to one endpoint than the other, and then most of this loss and the random loss is in the last mile path segment near the client. Class 1 represents where PEPs are commonly deployed today in wireless last mile segments in satellite and cellular networks. Now, what's interesting in class 2 and class 3, where BBR v3 benefits, but QUIC does not. What's interesting is that there's two classes where BBR v3 benefits, but QUIC does not. So class 2 is asymmetric, but both of these path segments are lossy instead. In the real world, this might represent low resource networks or regions in developing countries with no IXPs. Class 3 is also lossy on both path segments, but the delays on either of these path segments are more evenly distributed. This represents, for example, high delay satellite networks where the middle mile is the lossy path segment. And interestingly, traditional TCP PEPs are not commonly deployed in these two classes of network settings, which makes sense given that QUIC wouldn't have benefited anyway. Rather, in class 2, stable internet connectivity remains an unsolved problem. And in class 3, what we know about satellite networks is that they often deploy proprietary protocols that do little more than simple connection splitting on these lossy middle miles. So this finding suggests that with newer versions of BBR, these new types of networks may actually be able to benefit from connection splitting, even though they did not before. All right, for our final finding, we realized that these congestion control heat maps can also be used to kind of characterize a congestion control scheme in an end-to-end setting. So here we have QUIC and BBR over time for TCP. And while QUIC and BBR differ significantly from each other as expected, even within BBR, it has become more sensitive to loss over time. And this reflects the idea that BBR is increasingly incorporating loss as a congestion signal. So in this third experiment, we find that the QUIC implementations of the same congestion control schemes vary significantly, so across each row. And they further differ from those of Linux TCP. If you look at each row of this graph, you can see, for example, that the BBR v3 implementations exhibit significantly different behavior from each other, and even an older congestion control algorithm such as QUIC can differ significantly depending on the specific QUIC implementation. Congestion control research on BBR especially largely refers to its implementation in Linux TCP. But these results suggest that some of these findings cannot be directly extrapolated to QUIC depending on the implementation. The varying behavior of these different implementations of the same algorithms have implications for how they would behave if they were split. We applied the split throughput heuristic to estimate how these different QUIC implementations would behave if they were theoretically split. And as we can see, it can differ significantly based on implementation. We think this variation has to do with the fact that QUIC is implemented in user space. This gives developers significant leeway in interpreting a particular congestion control standard and how they want to implement it, and also introduces more opportunities for variations simply due to bugs. Now, since QUIC is in user space, we weren't able to use an explicit connection splitter to actually measure the split throughput, since we'd have to implement a different splitter for each of these QUIC implementations based on their different APIs. However, because we used the heuristic, we were still able to get a representative measurement for the split throughput with much less developer effort. And this tool can be used in future studies of connection splitting. So what should be the takeaways of this presentation? First, with regards to end-to-end congestion control, we saw that different implementations of the same congestion control schemes can vary significantly. We urge the community, the research community, to refer to congestion control schemes not just as BBR or even QUIC BBR v1, but by the full combination of implementation, protocol, algorithm, and version. We also believe it would be helpful to standardize what it means to say that an implementation conforms to a particular congestion control standard. One way to do this might be to create performance test suites for a standard. As for the topic of connection splitting, this study has shown that there's still significant performance benefits to be gained from PEPs. We should find ways to emulate these performance benefits without the downsides that led protocol developers to encrypt their transport headers in the first place, which is a lot of what my dissertation was about. We also need real-world studies to validate whether these benefits exist in practice, and also to study other performance metrics that can be improved by PEPs. In summary, we found that TCP BBR, while it didn't initially benefit from connection splitting, has evolved to benefit more from splitting over time. Its current version, v3, benefits in settings, even where TCP QUIC does not. And also, QUIC congestion control implementations exhibit substantial variability from each other, having implications for how they might behave differently if split. All our code is on GitHub, and we hope people can check it out and evaluate their own congestion control implementations. Thanks.